Okay, here's our roadmap for today. We'll start with a welcome to infrastructure abstraction, look at the infrastructure management problem, climb the layers of infrastructure abstraction, walk through a real-world deployment example, check out the business benefits and ROI, and wrap up with future trends and takeaways. Let's dive in.
Welcome to Infrastructure Abstraction, defining the framework. To kick things off, we really need to pin down exactly what we mean when we talk about infrastructure abstraction, because it's a fundamental shift in how we treat computing resources. For decades, managing infrastructure meant literal physical interaction. System administrators had to rely on manual console configurations, pointing and clicking through clunky graphical interfaces, or writing custom and honestly pretty fragile scripts. Abstraction completely flips this paradigm on its head. We've moved away from that manual intervention and shifted toward machine-readable declarative definitions and programmable interfaces. We're now managing compute, storage, and networking entirely through software abstractions rather than ever touching physical hardware.
Section 2. The Infrastructure Management Problem. The Nightmare of Raw Management. Now, why did we even invent these abstraction layers in the first place? To understand the cure, we've got to understand the disease, which is the absolute nightmare of managing raw infrastructure at scale.
Without abstraction, organizations run into some seriously crippling challenges. You've got the noisy neighbor problem in shared environments, where one heavy workload hogs all the compute from another. Then there's configuration drift. That terrifying scenario where staging and production somehow become completely different, and your app crashes on a Friday night, waking you up with a 3 a.m. pager alert. We also face manual provisioning bottlenecks that just destroy developer productivity. Vital knowledge gets siloed in the heads of maybe 2 senior engineers, and managing complex multi-cloud network topologies, that becomes practically impossible to secure.
Section 3. Layers of Infrastructure Abstraction. Climbing the stack. Let's actually head to the stack and see how this all builds together. We're going to climb these abstraction layers step by step, and you'll see how each layer neatly solves a specific set of problems by hiding the complexity of whatever is right below it.
This timeline really maps out our evolution perfectly. Back in the 2000s, we relied heavily on raw bare metal. By the mid-2000s, virtual machines came along and revolutionized resource sharing. Then the 2010s brought us containers, which completely standardized our environments. The late 2010s gave us Kubernetes to orchestrate all of it. And today, sitting here in the 2020s, we are entering the era of serverless computing, where the infrastructure is almost entirely hidden from the developer.
But hey, let's not forget our roots here. Abstraction doesn't mean the hardware just disappears. Bare metal absolutely remains our foundation. For workloads that require massive I/O, ultra-low latency, and high throughput, think massive databases, you still need 100% resource ownership. That means leveraging dedicated multi-core CPUs, local NVMe SSDs for lightning-fast storage, and ECC RAM to prevent silent data corruption. Always remember, there is no cloud. It's just someone else's extremely optimized physical computer. The physical layer always matters.
So, our first massive leap in abstraction is the Virtual Machine Monitor, or hypervisor. The VMM is a software layer that sits directly over that physical hardware and creates multiple, totally isolated virtual machines. It abstracts the physical CPU, the memory, the disk, and basically tricks each operating system into thinking it has its own dedicated computer. This was a game changer because it drastically improved hardware utilization. Then we evolved to containers. If virtual machines abstract the hardware, containers abstract the operating system. Technologies like Docker let developers package their application and literally every single dependency it needs into a single portable unit. This is huge because it guarantees that if the code works on the developer's laptop, it's going to run the exact same way in the cloud. It finally, once and for all, eliminated that classic developer excuse of, well, it works on my machine.
Now, managing 5 containers manually is easy enough, right? But what happens when you have 5,000? That's where Kubernetes comes in. It's a container orchestration platform that acts as the ultimate traffic cop. It completely automates deployment, seamlessly scales things up when traffic spikes, and even provides self-healing fault tolerance if a container suddenly crashes.
To manage this incredibly powerful stack, we turn to Infrastructure as Code, or IaC. IaC is the practice of managing your entire IT infrastructure using declarative, version-controlled files. You just write a file stating exactly what you want your infrastructure to look like. Let's say 3 web servers and a database, and the execution engine just makes it happen. Because it's code, it's totally repeatable and testable.
This naturally fuels practices like GitOps, where your version control system acts as the single source of truth for your entire infrastructure, wiping out manual configuration drift for good.
When we formalize these abstraction layers within a broader framework, we step into the world of platform engineering. By combining container orchestration and service management, organizations are building internal developer platforms, or IDPs. These platforms provide a unified, self-service interface that simplifies resource allocation across complex, multi-cloud environments. This really sets the stage for higher-level service orchestration and seamless API management.
Section 4. Real-world deployment example, the modern developer workflow. So all this theory is fantastic, but what does it actually look like in the wild? Let's apply this theoretical stack to a practical, modern developer workflow to see the abstraction in action.
Here is where the magic happens. Step 1. A developer simply commits their application code. This instantly triggers an automated continuous integration and delivery pipeline. Step 2. Our infrastructure as code engine kicks in, validating the syntax and making sure everything complies with security policies. Step 3. Containers are programmatically provisioned and then orchestrated by Kubernetes. And Step 4. The application is live. Zero manual server configuration. The developer never even had to touch a console.
Section 5. Business benefits and ROI. Why the enterprise cares. The crucial point here is understanding why enterprises are investing millions of dollars and countless hours into climbing this abstraction stack. What is the actual return on investment at the end of the day?
Looking at the key metrics improved through IaC implementation, the impact is absolutely undeniable. By codifying infrastructure, organizations aren't just speeding up deployment. They're fundamentally reducing lead times across the board. They're catching failures before they even happen, slashing their change failure rates, and turning disaster recovery from a frantic multi-day nightmare into an automated, rapid process.
Ultimately, abstraction gives enterprises a strategic superpower. It delivers blazing fast time to market while simultaneously guaranteeing strict regulatory compliance, because all your security policies are codified. It breaks the chains of vendor lock-in through platform-agnostic interfaces, significantly slashes operational overhead, and introduces the rock-solid reliability of immutable infrastructure.
Section 6. Future Trends and Takeaways. The Next Frontier. We've covered a ton of ground, but technology never sleeps, right? Let's look out at the horizon and see where infrastructure abstraction and platform engineering are actually heading next. The future is looking incredibly cool. We're seeing the rise of unified, cross-platform IaC solutions that can manage AWS, Azure, and Google Cloud simultaneously. We're also seeing advanced API abstraction layers and the next evolution of platform engineering, where AI shadow agents act as localized abstraction layers. They are literally stitching large language model outputs directly into automated infrastructure actions and dynamic API calls.
Okay, let's do a quick recap of our journey today. While we absolutely use software to hide operational complexity, raw physical hardware remains the undeniable performance foundation. Virtualization and containers step in to successfully hide that hardware from the developer. Then, orchestration tools like Kubernetes and IaC completely automate the deployment lifecycle. Bottom line, abstraction is the engine that drives modern enterprise speed, security, and scale.
I want to leave you with a bit of a provocative question to think about. As these abstraction layers continue to mature, and as artificial intelligence becomes more and more deeply integrated into platform engineering, how long will it be until AI can provision, manage, and secure our entire global infrastructure completely autonomously, without a single human intervention?
The future of IT is automated, and honestly, the sky is the limit here. Simplify your infrastructure, keep building faster, and please don't forget to like this explainer, share it with your fellow developers, and subscribe to our channel for more deep dives into DevOps, cloud, AI,